Hello, I'm Doug, and this is a talk that I gave to BarCamp Boston in April of 2009. A BarCamp meeting is self-organized, and I wrote up on the sticky note that I wanted to talk about visual physics, working on new ways to see old physics. And I had about 20 folks in the room. A few of them did drop out because this is really heavy going at times. Lots of new ideas shown in a small amount of space. So this will be a challenge to your brain, and I hope you enjoy it. This first slide, actually, if you can kind of get an appreciation of it, that will be very important because it really deals with how to visualize quantum interference. Now, we really know the math for quantum interference very well. In fact, in the world of math, it's not that tough. What has been actually impossible so far is to come up with an image of what is going on that actually makes sense. And we will get back to this image later on, but there's at least a chance that we can make progress on that sort of issue. So what I'm going to do in this talk is cycle through physics, math, and programming. Now, you may be more skilled in one of these or the other, so if that is the case, please be patient while we come back to that subject at hand. So while we're kind of going through one of those tougher subjects, what I want you to do is just kind of get an appreciation for the issue, even if you don't have a real comfort level with it. At least you'll get a sense of what's behind the topic at hand. And we're going to circle through this 3 times, first going over the problems in physics, problems in math, and problems with programming. I will then detail some new things that I do in these 3 areas. Then there will be an interlude where I actually apply some new physics and math programming all together. I actually need all 3 of them in order to make some insights into quantum mechanics. And then I finish up with a request for people's own contributions to this type of study and this type of area of work. So we start with a physics problem, that gravity does not get along with quantum mechanics. This problem was completely clear to folks working in the 1930s. The problem was popularized by Stephen Hawking in his book, A Brief History of Time, and then the subsequent movie, which is also, I think, on YouTube. Now, those two do not get along on a mathematical level because, well, is there a short answer to why they don't get along? Well, I think that would be that gravity has to do with what we call geometry, kind of how we measure the distances of things, and quantum mechanics is about operators and things coming in clumps yet being wavy at the same time, and the math machinery of clumpy wavy stuff just looks like it has nothing to do with the mathematics of measurements changing a little bit as you move around in space-time. Now, current work is going on with strings in 10 or 11 dimensions is now the current way to work. If you go to my website, visualphysics.org, you'll see my slams where I have more against the folks working with strings than almost any other. I think my favorite one is that if your theory is wrong, then it can be made arbitrarily complicated. I don't believe you are smart enough to understand string theory, because no one is smart enough. And that strikes me as not being the way nature must work. Nature is got to be very simple, if somehow extremely confusing at the basic level, and that's my goal and kind of the things that I work on. Loop quantum gravity is another kind of smaller group of folks who actually think that geometry is number one, general relativity is number one, and they're trying to figure out then how to pull out the kind of operator world that is so prevalent in quantum mechanics. But neither of these approaches actually makes a specific measurable prediction about gravity, and that is a huge flaw in those areas of study. Well, there's another big physics problem, and that is mass. And I say it is FUBAR, which stands for fucked up beyond all recognition at all scales. Because if you look at the atomic level, that would be the standard model, and the standard model works perfectly so long as no object has any mass. That might seem silly, but it was great at predicting the huge number of particles that were out there, and even said, hey, you're missing a few over here, there, and this other place, and it was spot on. But of course, the physicists understood that all these particles had mass, and they had to find a real fancy way to get the mass in without breaking what they already had. And that would be the Higgs mechanism, otherwise known as the Mexican hat dance, where you say, oh, there's a false vacuum here, and it's doing an awful lot of stuff. I personally don't think vacuums can accomplish a thing. So there is an actual $8 billion bet at the LHC collider in Geneva that says they will find the Higgs, and I'll put my $20 up that says they won't. Now, at the scale of galaxies, looking at the rotation profile of thin disk galaxies, gravity doesn't work. Because if you were to just give it a nudge on the center axis, the math predicts that the galaxy should just collapse into a ball. Now it doesn't do that. The solution should be stable, but it's not in the current form. And if you look at the gases that are way out on the outer reaches, Newton's theory of gravity predicts that those velocities should be slowing down as you go out. Now they don't. That is the observation. Velocity is stable, a constant, once you get to the outer reaches of galaxies. And the current popular hypothesis for explaining this is called dark matter, where they just add as much dark matter stuff as is needed to make the galaxy both stable and have these little light gases go at a constant velocity. On the universe scale, we only found out recently that it seems to be accelerating. We've got no idea how it's pulled off this trick, so we call it dark energy. And then as far as the origin of the universe, that would be the Big Bang. And classical Big Bang theory has two problems. The first is that it is mathematically unstable. So you have to get your numbers right to like 100 significant digits so that the galaxy will last as long as it has. And that seems really ridiculous. And there's a problem that, according to the cosmic background radiation data that we've received, everything is going at exactly the same time, like 100,000 years after the universe was born, and yet they were kind of too far away from each other to agree to that speed. Now, I have written this in a suggestive way, calling both the galactic and Big Bang kind of problem stable constant velocity solutions, because I think that's where I think the problems really are the same, kind of in a mathematical kind of sense. As far as the Big Bang problem, the favorite hypothesis there is known as inflation, and it needs this really weird, super amazing stuff or vacuum to do amazing stuff in order to get around these types of problems. So we've got, according to our hypotheses, 4 different kinds of super weird stuff out there, and I think if we get our math right, we'll have none of those weird sorts of material out there. Let's shift to a math problem. The real and complex numbers are actually fabulous. They are beyond beauty in their utility and their reach. And for 4 dimensions, it's not nearly as nice a story. Formally, the real and complex numbers are known as mathematical fields, meaning that they have addition, they have subtraction, they have multiplication, and they have division. It turns out that it's the division that is the tricky one to get, and people in a hurry just say, oh, it's not that important, I think I'll just take plus minus and a little bit of multiplication, that should be fine. That's not what happens with the real and the complex numbers. They're really important to have. And the reason they're really important to have is that it's required in order to do calculus. Now, what people do is they make some kind of algebra, just constructing it together the way they would kind of like, and then they put it over the real and the complex numbers in order to do their calculus in a proper way. Now, physics is the study of change in space-time. And so it seems to me that we should be doing 4D calculus throughout everything that we do. So I asked this crowd for a show of hands. I said, how many of you know the 4D field's name? And out of about the 20 people, I expected about half of them to know. But it turned out that only one person could name that field, and it is known as the Quaternions, as in 4 Roman soldiers. And yes, I own quaternions.com, a site which really is dedicated to teaching how to use quaternions to solve problems in physics. This visual physics site is kind of more community-based, trying to put together a group of people to come up with fun pictures to show people. So what are the limitations of quaternions? Well, right now, you cannot do Dick with quaternion derivatives because quaternions do not commute. Now that's kind of odd because you can do amazing things with 3 formal subgroups of quaternions. In other words, there are 3 complex numbers within every quaternion. And this makes no sense to me because I could repeat every single proof done in complex analysis with a quaternion of the form A, B, 0, 0. So I go through this whole exercise, do all these super nice, cool proofs, and then when I say, hey, I just shifted my reference frame a little bit and these factors have gone over here, well, it kind of starts to break down. And that's really bothersome to me. Now, there's another math problem that you might actually be able to relate to, and that is that real and imaginary numbers look the same in the complex plane, but they clearly are not the same. If we take 1 and we square it, we get plus 1. If we take I and square it, we actually get back to the reals, minus 1. Now, in the complex plane, what they do is they put, the real axis horizontal, the imaginary axis vertical, and you say, what's the difference? And they say, well, just rotate it 90 degrees. Isn't that simple? Well, it's simple, but it's too simple. Because real numbers aren't imaginary numbers. Let me show you another way that they're different. This is with graph theory, where you label a vertex, you make a line and put a label on that line to get to another vertex. So with the real numbers, you've got a vertex where you've got 1, you've got an edge with a label 1, so 1 times 1 gives you 1. Real numbers love themselves. They come back to themselves. Now you look at a complex number and it's got the real on there, but the imaginary number involves directional edges. Now you can show that by taking the 1, multiplying it by I to get out to the I. Now to get back to the 1, you take an I and you have to multiply it by minus I. So of course minus I is not equal to I. Those edges are different. And there is no loop for I that has another I that gets you back to an I. So there really is a difference between the two, and I think we need to come up with a visualization that reflects that difference. And I would even go out on a little limb here and say, if your visualization doesn't show unambiguously that there's a difference between real numbers and imaginary numbers, then your visualization is technically wrong. Now, the complex plane has been repeated in so many textbooks, and here I am saying I think those textbooks are technically wrong. But that's the way it goes when you're trying to do research in math. So now we turn to a problem in programming, and that would be animation and video formats. There was developed GIF 89A for doing little joke animations. It's really old technology. The files tend to be kind of big, and if you open up a bunch of these in a browser, you can actually kill the browser. They came up with a strategy that was modern, this thing called Ming, but Firefox folks decided to cancel it, and it's the one example I know of where they pulled a perfectly working technology. I know because I actually built a few Mings. They worked great until, as I say, they pulled it out of Firefox. Now, there are a bunch of proprietary formats out there. There's QuickTime, there's Windows Media, there's DivX, there's MPEG-4, there's Real Media, there's Flash, there's Moonlight. OGG actually doesn't belong in the list. It is an open source effort, but they've had some troubles getting, to the end line, as it were. And it's frustrating dealing with video on the web because there's so many people competing to be number one. Why is that? Well, I think it has to do with money. Both from Hollywood and from porn, because gee, if you can show a small animation of anything, well, then maybe you can get those people to pay for it. So those are the lists of problems, and now I'm going to go on the new cycle and start with new physics. I'm going to show you variations on the Maxwell equations, which govern how light works, by upgrading tensor formalism. Now we can starting from the what's called the action of the Maxwell equations. The Maxwell equations are the things that show up on the t-shirt "and God said." And what's really neat about knowing how to actually do this is that you'll be able to say, I understand why God had to say the Maxwell equations. And what I did for the live audience was to hand out a derivation of the Maxwell equations in detail that is actually in a post on the visualphysics.org website. And if you're interested in that kind of detail, it's really a wonderful, beautiful calculation. I highly encourage everybody who has some interest in math and can do Sudoku. It's technically not that difficult. It's usually not written out in detail because it just takes a lot of LaTeX sort of typing. But I've done it, and I want to share it because it really is gorgeous. Now, if you're skilled at the arts of analyzing actions, you can actually look at that expression and tell that it conserves energy. The way you do that is look at that and say, do I see a t kind of standing there by itself anywhere? No. Therefore, I can vary t and not really change the variation on the action, and therefore there must be a conserved quantity, and that conserved quantity is energy. So once you learn this, it's kind of amazing. You look at it and go, no t conserves energy. It seems kind of simple. Do you see any x there? Well, there is that dx sort of thing, but that's different from just an x, okay? And because you don't see an x, it conserves linear momentum. Do you see any angles in there? Nope. Good. Then it conserves angular momentum. Do you see a little subtraction going on there? Well, that subtraction is necessary in order to have gauge transformation kinds of properties, and it actually is related to conserving electric charge. So just by looking at it, you can realize all these sorts of things. And now if somebody says, I'd like to do something more, well, they're in a rather tight situation here, because there are all these conservations, and if you just do a little bit, you're extremely likely to mess it up. So, as long as you studied your Eastern philosophy, if you really want to do more, you do so with less. And I basically got rid of the Greek letters, which is nice. Except people would say that makes no mathematical sense. Aren't those tensors? Those are tensors in 4 dimensions that also can be multiplied and divided by each other. We're granting them additional powers. They actually are growing up into quaternions. But then you go, hold it. If I can just multiply those two together and then I subtract the same two, I bet that's 0. So I have to make one other little change in here, throw in some conjugates. And if you're good with quaternion multiplication and going through all the detail, then all the little terms that show up in this exercise, using this as quaternions and this as tensors, are exactly the same. There is not one term or one sign different from this written in the tensor formalism and this written in the quaternion formalism. So you say, then you have accomplished nothing. Right. But now I have additional powers. And I'm going to try to use them wisely. I'm going to use them actually to get different symmetries in this action. And by having different symmetries, then I have different things conserved. And what I can do here is change this thing to the symmetry that shows up in the weak force. It's called SU2, which is the unit quaternions, and this is one way to write it. And then there is U1 cross SU2, that is the second line, and the third line actually has 8 elements to it, and I think that's going to be a way to represent SU3. And so now I've got 3 of the 4 known forces, symmetries in my action, and that would be electromagnetism, the weak force, and the strong force. And so that leaves the question of, well, how about gravity? Well, gravity is about metric. It's been proven that if you go to different places, that metric changes. A metric is symmetric. So if you have symmetric metrics being different, the difference must also be symmetric. Well, that doesn't work for quaternions, because quaternions have this anti-symmetric curl thing inside them. They can't get rid of that. So I won't do it here, but I certainly have discussed elsewhere about using hypercomplex numbers exactly sitting in the same chair as the quaternions do in this expression, and then this does have the ability to describe much more symmetric situations, which you need to do if you're going to do gravity. And there are other really critical details, particularly with the current coupling term, that had to be worked out in order to convince nerds about that this is a fine way to go. In fact, quite elegant at that. So here's another bit of new physics. The constant velocity solution for gravity using the product rule. So we're going to combine Newton's gravity theory with real rocket science. Real rocket science involves the product rule of calculus that says the change in momentum is the summation of mass times acceleration plus velocity times the change in mass. So we've written it out here, and one of the cool things is to realize, to make this a valid vector expression, the rocket term has to work in the v-hat, and if that's working in the v-hat, then we have to have a v-hat expression on the other side. So many years after Newton, we're saying not only does it work in the r-hat direction, but it also must be working in the v-hat direction for when one of the effects of gravity is to, throw masses around. The problem with applying this to galaxies is they don't change very much. They're stable for hundreds of millions of years, and they aren't like a rocket, spent in like under 30 seconds or something like that. So I have seen papers where they have gone through the calculation to say, this really is totally and completely and thoroughly unimportant. And I respect people for going, I don't think so, but let's do it anyway. But nature sometimes gets a little creative on us, and I'll show you one idea I have here. Watch that VDM-DT-V term closely. I put a dr in its place and then got the units right with the c. So what this is saying is that the effect of gravity when the velocity is constant is to determine where the mass is in space. And I think that's basically what goes on in a galaxy, particularly in the outer reaches of the galaxy, is that the velocity is now constant, but the mass is actually changing quite a bit. Now there is a huge omission, and that is I haven't been able to apply this to a valid collection of data. You know, the galaxies or the Big Bang, because it really is relativistic rocket science, and that's a tough thing to do. So let's move on to new math. We can define a derivative of a quaternion function. Here is the standard limit definition. And you can write that little differential element on the right, or you can write it on the left, and the problem is that they're not the same. And there are people who work with left or right derivatives, and what they have to say are silly things like they can't show that a function like q squared is analytic in q. So I think that is so useless as to say, inspire me to go and try and find a far better solution. And I think I have. What I do is I use two limits and get basically a directional derivative along the real axis. The way this works is that the 3 vector, that thing that causes the right-hand rule that causes the problem, I say let that go to 0 first. And then I'll let time go to 0. And if you take that attitude, then writing the little differential on the left or writing it on the right will end up with exactly the same answer. And this is why I see this big circle between physics, math, and programming. In this case, I've been talking about a definition that's purely math, and yet it has consequences for physics. And the reason is, if I think of the 3 vector as being changes in space, and the change in the scalar being a change in time, then by saying that the changes in space are smaller than the changes in time, I'm literally saying that the speed that it takes to go from one event to another is less than the speed of light. And I think this is the domain of classical physics. But that just brings up the question, well, what happens if you reverse your little 2 limits? And if you do that, then you get that problem back where you don't know whether you should write it on the left or the right. But you can take the norm of this, and the norm of this sort of thing is the same whether you write the differential on the left or the right. Now, this is not a well-understood area of, well-known area of math, but there are mathematicians out there who have studied the norms of derivatives. And all I'm saying is that when you use this reverse sort of story of the limits, then you're in this norm of a derivative. So this applies to space-like events, where the changes in space are larger than changes in time. Now, this does not mean anything goes faster than the speed of light. No, this just means that we're dealing with a set of events that have space-like separation from each other. And I believe that this might be the domain of quantum mechanics. So this might just be a thoroughly amazing result that we have a completely mathematical reason for the difference between classical physics, that being the regular derivative or derivative along the real axis, and quantum mechanics, which is a norm derivative for space-like separated events. So that would be the whole reason why we have this division between classical physics and quantum mechanics, that when we do the calculus of space-time correctly, we have this natural division between a directional derivative and a norm derivative. So we can now address that problem we remember for so long ago about real reflections and imaginary reflections. Here is the animation, and I've added a lot of labels in here. I found that understanding animations was very difficult. That middle top graph, if that's all I had, it was really necessary to surround it with things that kind of, in a way, moved less, that left marks on the screen that my slow eyes could kind of stare at for a long period of time. So on the left side are three complex planes. The ty is basically up and down versus time. Then there is near and far, the z versus time, and the left and right versus time. And then I also wanted to see all possible states that the system could be in. And that was inspired mostly by quantum mechanics, which has this notion of a wave function that really describes everything place a system can be in. And then I do a random sampling of those states. And this kind of steadily moving thing, even though it was very simple to set up, because it was just quaternion addition, again makes a connection to physics, because that is an inertial observer. So the simplest act you can do on a quaternion, add it to another one, makes a connection to a deep notion in physics, and that is inertial observers. So now we're going to think about reflections. And an imaginary reflection means you have a plus I and a minus I and a plus j and a minus j and a plus k and a minus k. And whenever you do that, you get a pair of events on the screen. And we see these 2 points, and they are moving towards each other and crash and burn and go away. And it's one of the great ironies, I think, that we've actually got the imaginary axis reflection absolutely correct. What we messed up on is this one, what the real numbers. The real numbers have this property that you have to remember what they just did. Okay, so here it's going, and it's going up to 0, and now it goes back the way that it came in, and you have to remember all that kind of stuff. And you can only see one dot on the screen at the time, and that's qualitatively different. You know, you look at this one, you go, oh yeah, that's the pair of dots. Oh, this is the one that's going in, and then it goes out the way it went in. Those are visually different, distinct. And you can actually do a reverse of both space and time, and that's in red. And the funny thing is, it looks like it's continuing on to the future. And I'm not quite sure exactly what all the implications are of that, but it is kind of fun that reversing both time and space makes it seem to go forward. So now I want to talk about some new programming that I've done. There are these things called the command line quaternions. The programs are really small and robust. They can be piped together and be combinatorial. We make a whole bunch of these things and we sort by time, and then we can graph them using this point of view ray program. So let's see if I can get this to work here. So here we are at the command line, and I've got lots of functions, too many to list it looks like. So let me just look at qadd, and add n minus help to see the directions for using this, and I go q add n 1 2 3 4 5 6 7 8, and let's not do 100, but let's just look at 10, and we see all these numbers go up on the screen. And what I can do, since these are all pipables, I can just take all these things and I can say take the conjugate of them all, and you'll see that a whole bunch of minus signs show up, and that is actually space reflection. And if I now take these guys and multiply them all scalar by -1, then you see that it's actually now the first number that appears there. Time, that's what time reversal is all about. And if I want to see what space-time reversal is all about, then I get rid of this conjugate, and there is my space-time reversal. And what I can then do is put quotes around this sort of thing and call my program Q graph. I actually had to put a whole bunch of other sorts of things to get this to work. If you want to actually download this and work it, go to the website that downloads. I've got some YouTube videos on really how to work with this at the command line. It's not that easy. It will take work to get it to go, but I think at least in my hands it is a lot of fun when you can finally get an animation out of it. So that is command line Quaternions, a very brief demo. So we also have been able to construct a new website, visualphysics.org, that I've already referenced a few times. There is a manifesto section that goes over my guiding philosophies, a tutorial section which has a lot of YouTube videos to help explain what's going on. The heart of the site is the animations location. There's also downloads, forums for, I hope, will become an active technical community covering math, physics, and programming. The financing is to discuss a little bit about the money that's behind this, and it is really a little bit of money. It's a little bit that I can afford. And then finally slams, where we actually have some fun at the kind of difficult situations that other people working in these areas face. That is part of the fun of doing physics, is actually making fun of other folks, their work, really, not them personally. All right, and we've got a Drupal backend. Let me just go over to the site, and we'll just, as you can see, it is very visual based, kind of looking. We've got this many animations, and who knows, in a few years time maybe we'll have thousands. That's my dream. And all you had to do to get kind of take a closer look at any of these is just click on them, and that will bring a thing that has the the title of it. So this is apparently the group SU2, and as I like to say, this looks like Mrs. Pac-Man in 3D. So let's watch this. It starts at 8 points, as you can see in the shadow, grows into each other, forms a ball, and then shrinks to nothing. So little summary, a description. If I've got a YouTube about this particular topic, then it's there. I show you the math that I think symbolically what I'm dealing with. There's this great project called Sage, which is trying to be an open source kind of thing for that does many of the things in Mathematica, and I actually do occasionally get around to creating a site over there. And let's see if this and I'll see if I can pull that one up, or whether that site's a little flaky. Let's see, not yet. All right, we'll see if it shows up. This is actually all the numbers in that animation. And I don't know about you, but I can't figure out what's going on here. Well, actually, I suppose it doesn't have that many negative numbers, and it has a lot more positive numbers, so we can get that sense. But it's kind of crazy that this collection of numbers is exactly what makes the animation. But that's part of the fun of dealing with this topic. Let's see if we got it. Oh, yes, we do. So if you are a fan of Python, then this will look pretty simple to you. And I just take this because of this kind of attitude, because who knows, maybe you are more comfortable in the Python world and doing things in this way, and so maybe we can reach out to you in that way, and any way that we can is good news. So these banners, as you go around, let me just mention one thing about the finances, in the sense that I am interested in your time, so there is a sign-up incentive, and you get this Nerds No bumper sticker if you sign up, which is somewhat unusual. If you actually start making animations, you'll get a button. Well, pretty amazing. Okay, and a $10 check. And believe me, you will put much more than 10 hours into this. And then there is the director incentive. If you can conceivably put together 100 animations, that's quite a bit of work. And yes, I do request money if and you know what, I really don't think I'm going to get anything. so but it's there. Okay, it's like kind of like buying a lotto ticket. Well, I tried. All right, so the slams, as they say, if you feel like making fun of folks, work, not the people. Just we got, black hole math is bogus. So I could go on. You could ask me about any of those sorts of things on the forums page. The forums page is got physics, programming, math, manifestos, and then this open independent research. This is kind of where I put my unified field theory work. And so if you want to see the latest of what I'm thinking about and want to engage me in that, certainly come here and click away. These if you see a banner that you think was interesting and you just want to find it, then this page actually shows them off, and you just click on it and you'll just go there. What is this? This is just the animations, I believe. Let's see. Yes, it's just the animations, the equations, the title, and they just kind of go on like that. I believe, yeah, several pages, something like that. All right, so that is the site Visual Physics, and I really do hope more folks decide to come here and put some time in. You'll get weird little animations, and it's just fun to try and figure out what the heck is going on here with these kinds of things. So let's go back to the talk, which would be over here. All right, so this is where we get to the new physics, new math, new programming. There's an experiment called the delayed choice experiment in quantum mechanics, and one of the guys who really got it done in the lab is this guy named Alan Espé, and he was at MIT just a few days ago, and he's just really amazing in what he can accomplish, because Wheeler described this as a problem and Espé actually got it done. Now the light source that they use is described by sines and cosines, which are very regular. And what we need to do is to look at complex numbers that involve sines and cosines. And only when we really understand a complex number that has sines and cosines are we going to be able to understand why this most unusual kinds of stuff seems to happen. So I actually discussed this in a forum topic, and hopefully it'll come up soon. Because Espay is very clear that he does not. He understands why the math behaves the way the math behaves, but there isn't a visualization out there that seems at all reasonable. In fact, he kind of ends it with if it goes this way, then it requires that the photon goes down one direction or another direction, and then when I do this thing, it's also the case that it goes down both, and that logically just makes no sense, and yet that's where he's left. So right here is the wave function. Now the wave function is something that you never get to see, okay? And that's the way quantum mechanics works. You never get to see it. What you do get to see is right below it, the square, okay? That's what you get to see when you take the conjugate of one and multiply it by another. And in this case, you end up seeing 1. So you multiply your one wave function by the conjugate of itself, and you're certain that it's there. It's quote-unquote normalized. All right, so this is actually cut and paste out of Espay's paper, and you see these nice up and downs kinds of things. This is when you have interference, and this is when you don't have interference. And what I set up as a hypothesis was that if I really understood my math machinery well, then I should be able to recreate this type of image. And I made some good progress along this way. So let's just see that. All right. So here is a picture of, let's see, this equation, the cosine, the sine, the 0, 0. All right, so the wave function, it does nothing in the y, okay? Nothing up or down. It does nothing near or far in the z. All it does is this x stuff. Now, if we think about what's going on right down here, it's changing a lot in x, right? Changing a lot in x, changing almost nothing in t. Well, that's like, isn't that faster than the speed of light? It's like, yeah, because this is a math construct. This is not saying this caused that, okay? It's just the wave function is something a math wonk can come up with, and we can't see it, okay? But we can take this norm thing and then see it. Or see its probability density sort of thing. So, I'm having trouble with that thing down there. So now, and there's one other important detail, and that is that I made this up in such a way that that there are a bunch of phase changes in here. There are a bunch of shifts in the cosines and sines, but you say, but I can't see them. I feel disappointed. So what I did was I artificially took that phase thing and I also added it into y, okay? And you go, oh, but it looks kind of the same as you're saying that the phase is shifting as I go up. I say, yeah, that's exactly it. The phase is changing as I move up here, but it looks the same. And that's because this is periodic, which means that even if it were to start here, it would eventually go around and get to here and do the same darn thing all over again. So it's kind of hidden. The phase information is really kind of hidden. So I said, well, I wasn't happy with that, so I wanted to see it, darn it. And so I put in the red photon. Now, the deep lesson of particle physics is there is no like red photons. All photons are the frickin' same, okay? So this is just a programming hack so that I can get comfortable with the idea of he really is shifting the phase through here, because for each one of these red dots, t equals 0 and t never, changes, okay? So it's just like one sample out of the whole thing. But now what we can do is we can look for interference by taking the A is unshifted, B is shifted, okay? I can take the unshifted, star it, multiply it by B, and do the reverse, and see what that looks like. and then I'll take the unshifted guys, by themselves, and the shifted guys by themselves, see what it looks like. I can also work out the algebra there if you're an algebra fan, but here's the animation. And you go, oh, that looks just like a space graph. That's kind of cool. And we go, whoa. So we get all these particles like creating each at that step, and then they annihilate. Now, those words, creation and annihilation, actually are connected to something called the second quantization process in quantum mechanics. So it certainly looks like creation of pairs of events, and then we get ready for annihilation, and boom. So this, and now we can also appreciate why this is complicated to figure out, because what we had to do was now have these three different complex planes together to make this kind of interference stuff. We've got the loopy stuff going out here made of sines and cosines. We got Z actually doing nothing. And this actually should do nothing, except that what we did was we decided to put the phase in here artificially just so that we could see these different places, getting to going through this kind of process. So when you combine the two together, so when you look at one, watch this. This is pretty exciting. Boom, that's it. This is the guys by themselves. So this is unshifted against unshifted, and shifted versus shifted. It's like nothing. Oh, I know exactly where it is. And those are the two sorts of graphs that SPAE got. This is the no interference going on. I know exactly where everything is. And the, oh darn, there is a phase shift going on, and because I've combined shifted and unshifted, I get all these phase sorts of things. So this may be a new way to visualize one of the great mysteries of quantum mechanics. We'll see whether quantum mechanics wonks pick up on it, and whether they get excited as I am by it. All right, so let's start back here. All right, just a few more to go. About what you could do. Okay, you could participate at the site, visualphysics.org, which I notice I didn't write on this slide. Hey, sign up, you get that Nerds Know button sticker, which is numbered, by the way. So sign up early so you get a low number, and you can sell it someday on eBay for thousands of dollars. Run the software, the command line Quaternions, and you grab the actual code for how you write something, graph something, and just do variations. And if you've got enough energy, go ahead and post them back to the site. And just arguing on the site in the forums is also great, and I prefer you argue there than just send me an email in YouTube or something like that, because whatever questions you have, probably somebody else is worried about a darn similar thing or a slight variation on it, and we might be able to answer their question when they come by and look at it. So another big thing with code would be how to do like web-based animations, because this software is slow, because Pavre makes really pretty pictures by bouncing light all around. JavaScript, on the other hand, super fast, and I mean, I do have some JavaScript functions, but I'm not sure how to really make animations from there. There have now been announced several different 3D browser APIs that kind of connect to JavaScript, so it becomes possible to think of maybe using those with my Quaternions guys and putting together a bunch of things. Not sure, but worth an investigation. So you can also participate in the math, and I think really kind of in two ways. One is if you are actually in school, you can do what I did in a relativistic class, and that was keep two different books. solve it the standard way where they're talking tensors the whole time. Make sure you can do that, and to solve it using quaternions the whole time. Quaternions do not make the problem simple. Sorry, it's not a panacea in that way. It's comforting that you're using the same tool throughout, because you'll notice in physics they kind of change their jargon when they move in this problem and move in that problem. And if you use quaternions throughout, you go, oh, these are the types of quaternions I'm using, and I remember what I used to do with quaternions over there, and that's why that's a different area of physics. So you kind of get, by using the same tool, you get a sense of the relationships between different areas of physics. Or a different exercise would be to go through this book by Tristan Needham, Visual Complex Analysis, and wherever he writes an equation, you write an animation. If I had free time or time to put into this project, I certainly think that would be an awfully fun thing to do if you're into doing a lot of work. And if you're a physicist person, you could do relativistic rocket science. Now, this is going to require somebody who's awfully darn good with numerical integration, because we're talking about not being able to cancel away that mass that everybody is so used to canceling away, and then applying it to a complicated data set like rotation profile of a galaxy. So that is certainly another way. And finally, I ended with this slide about my personal stuff. If you want to know about me, I got degrees from MIT in biology and chemical engineering, not math, not physics. I did go and get a master's in software engineering. I'm working now at Black Duck Software, collecting open source software from around the world. On the web, I have a number of footprints that get various amounts of hits. Visualphysics.org is the newest one, and it's kind of the community-based sort of thing. There's quaternions.com, which is dedicated to doing physics with quaternions. It's much more kind of instructional. The software is being developed on SourceForge in the project Quaternions. It's called actually Command Line Quaternions. The standupphysicist.com is my effort at outreach, which has led to a good fraction of the 70 videos I have up on YouTube. That is my email address, so I really don't hide it too well. So I get some spam, but the spam filters are pretty good. And also there's the forums. I would prefer actually kind of you sign in to visualphysics.org and get into a discussion there, so your insights, your questions might be addressed in a slightly wider or more public way. I like having public debates over these kinds of things. So the 20 folks that were there, we had I don't know, maybe 25 or 30% of them walked out at some point, because this is a tough talk to follow. But the majority of people stayed for the entire show, and what was really felt good was that eventually some people came up to me later and said, I did a little work with quaternions and thought they could do more. And that is a common reaction to them. In fact, when they were born, there was a common reaction. We should be able to do more. And I'm just really working on fulfilling that and doing so in as kind of open way as I can. And if you can come to the website and make a contribution, big or small, it will be very much appreciated. Thank you very much.